Okay, we're going to look at the second problem here on this sheet. That is, a child is pedaling a tricycle at a constant speed such that she and the tricycle have 30 joules of kinetic energy. If her dad then does 20 joules of work on her as he pushes her, and the tricycle from behind, making her go faster, how much kinetic energy does she and the tricycle have now? Okay, so well, originally she has 20 joules of kinetic energy, apparently, and that's energy of motion. So let's see how this problem plays out. It's pretty tough to draw a tricycle, but I'll give it a shot. So here she is. Okay, so she's on this tricycle. All right, and there she goes. She has a mass, and just give it m, and then she has a velocity. Okay, and she's going that way. All right. Now, her kinetic energy here equals 20 joules. All right, and that's her 1/2 mv squared. All right, so there's her kinetic energy initially. Now her dad jumps in and does 20 joules of work on her as he pushes her and the tricycle from behind, making her go faster. Okay, so let's see if we could add in the dad somehow. So the dad comes in and gives a push, and that push is equal to 20 joules of work. Okay, so let's see how this works out. So this was I'm going to call this energy I plus W equals energy F. Now, if you had conservation of energy, then energy I would equal energy F. But what's going on here is you have the external addition of a work, all right, which is some energy is added into the system, so it won't be conserved. So in other words, the energy initially that she has plus the work done on her, okay, will equal the energy final. And that's what I start out with. And then I start to break this up, and I say, well, this will be your kinetic energy plus your potential energy initially plus your work, and then this will be your kinetic energy final plus your potential energy final. Well, potential energy is another topic, but I guess we have to cover it a little bit here. So you have potential energy, could be gravity. So gravity is a big one. That would be your mgh. And then you have your spring. Okay, your spring would be 1/2 kx squared, I think, something like that. So you have a couple types of potential energy. Okay, and then there's all kinds of energy inside the molecules themselves and so on and so forth, but that doesn't change, so it would just be on both sides of the equation, and it would actually cancel out. So we're looking at it from a larger scale at this moment. So and heat energy and all that, and sound, and we're going to say that there were no losses. Okay, so here we go. We have this here. Now, if he pushes her from behind, now let's fill it in. So initially she had 20 joules. Okay, 20 joule. Well, wait a second. What is this? This is the 1/2 mvi squared. All right, we're going to say she has no potential here. Okay, and this would be your 1/2 mvf squared. And she has no potential there. She's just moving faster. So she's going, this energy that we see going on here is all going to be moving energy. There's no changes in potential. Okay, what was the work that was added? Well, let's review plus the work. All right, so we have 20 joules here. All right, plus her dad, excuse me, she had 30 joules originally. I'm so sorry. And then the dad adds 20 joules. So there's the work being added. 20 joules equals 1/2 mvf squared. Okay, so how much kinetic energy does she have now? Well, the final energy is going to be 50 joules, so it just adds up. All right, but now we have 1/2 mvf squared. And then the question down below, it gives us the mass of the girl in question 4. It says, well, if she's 18 kilograms, so if the mass is 18 kilograms, how fast is she moving before her father pushes her? And then, well, let's see, before. So she had 30, right? 30 joules, okay, before. So before, she would have 30 joule. A joule is a Newton meter, okay, divided by, okay, 30 Newton meters equals 1/2 mv squared, okay? So how fast was she going initially is the question. Well, let's look at that. 30 Newton meters equals 1/2 18 kilograms times VI squared. Okay, a Newton is a kilogram times meter per second squared. And then we also have times meter over 1 here, Newton meter. Okay, equals 1/2 18 kilogram VI squared. Okay, so we would bring this up here, times 2, bring that down there, so we get 2 times 30 kilogram meter per second squared. That would be meter squared over second squared now. And then the 18 kilogram would come down, and that would cancel out kilograms. And then we'd have equals VI squared. Take the square root of both sides, and we get VI. Let's see. I get 1.83 meters per second. See, this meters squared, seconds squared comes out of that, and you would get, and VI would be plus or minus, but we're going, distance is plus, so we're going to have 1.83 meters per second here. That would be her initial velocity. Now, the question comes up in 5. If her father pushed her for 3.5 meters, how much force did he apply if the father pushed her for 3.5 meters? Well, this is then getting into another topic. Work is force times distance, okay? And so that work that he gave her would be, well, related to how much distance he pushed her. So he pushed her for 3.5 meters. So this distance would be 3.5 meters. And here's your force. And that's how we could dig into that. So let's see what we have here. The work that the father added was 20 joules push. Okay, 20 joule push. And so the force times the 3.5 meters equals 20 joules, okay? And then you would just divide, again, this is 20 Newton meters, and if you divide both sides by 3.5 meters, the meters crosses out, you're going to be left with newtons. And, well, it's 20 divided by 3.5. So, let's see. 20 divided by 3.5 is 5.7. So he applied 5.7. I'll keep it to 2 decimal places here because we were only given two significant figures in the beginning. We have two significant figures here. So it's 5.7 newtons is the force that he gave her over that distance. And I guess to finish out the problem, you would ask also, how fast was she moving finally? Well, she had 50 joules, and so if we wanted to find her final velocity, we multiply 50 times 2, that'd be 100 joules, divided by her mass, which would be 18 kilograms, and we take the square root of that, and that would give us VF. So we have VF here. Let's take that 100 joules divided by 18, and then take the square root of that. Let's see. Square root 2.35 meters per second. So she'd be moving 2.3. I'll make it 2.36, which rounded off to 2.4 meters per second. That would be her final velocity. And as you see, that is increased over 1.83. So it makes sense. It passes the common sense test that she started going faster, not slower, when her father pushed her. And the end of the problem.